Okay, so let's get started. So we have already considered a number of different methods, including some methods of supervised learning and even one method of unsupervised learning. And today we continue working with unsupervised learning methods. And if you look at a small table that I have in here, this is some sort of classification of whatever we have considered previously. And you may notice that we have these two columns, supervised learning and unsupervised learning. And here I have in rows the classification regarding classes that we have. So classes may be discrete or continuous. And probably you remember that when it's getting to supervised learning, we can have a classification problem if our classes are discrete, or we may have a regression problem when our classes are continuous. And we have considered both of these cases. For example, we have considered linear regression, and we have considered few classifiers like naive Bayes classifier or support vector machine or trees or forests and so on. In previous lecture, we have considered unsupervised learning for continuous classes, and that was dimensionality reduction. So we have learned how to transform from one space to another space, and we were aiming to get some smaller number of coordinates in the target space, and we were calling that dimensionality reduction. And today we are filling the last gap I have in this table, and we will consider the case when we have unsupervised learning and we will have discrete classes. And the problem that we will consider and that will fill this gap in our table is called clustering. So today we are considering the problem of clustering, and I will show you at least one method. If we have some more time, maybe I will show you something more. But at least one method I want you to know, it's called k-means. Let's start first of what is a cluster analysis. Cluster analysis or clustering, it's the problem of grouping a set of objects in such a way that we have some similar objects collected into one group. We should define somehow, of course, the similarity between our objects. In many cases, that will be some sort of distance in the feature space. So if we have our data points, they all are living in some multidimensional space. Each of the coordinates corresponds to the feature, to some feature we have, that we measure something, so that can be basically anything. And we are measuring some distance between these points, and we are trying to collect them together into some sort of groups in that space, and that will be the problem of clustering. Probably you might guess right now, where is this clustering useful for us? So can you think just off the top of your head of some problems that can involve clustering and that we may want to use it?
Well, basically when we just want to separate objects into some groups, but those groups are not predefined, we just need to look at the data and see how we can maybe separate them in a way.
What about some practical example? So I don't know, something you can use in practice. Think, for example, so let's say you have some online store, you are selling something. Can you use clustering? How would you use that?
Like maybe for some early stage of analysis of your customers to somehow divide them into groups and let the algorithm decide some kind of criteria how we can divide them. And then and then look at that result, supervise it, and make it more rational and make more sense in a way.
So,
I guess.
In many cases, you would like to group your customers into groups, And if you know that some customer belongs to some group, you will have some additional information on him. So for example, if you know that there is some group and it's buying some goods, so there is some list of what these people are buying, what are they mostly looking for. And you might think that if someone is classified into that group, you may think, well, I can advertise him some of the goods of this list. So you can probably guess if someone is buying something, that may be enough information to classify him to some group, and knowing that he belongs to that group will give you some additional information. What else can you propose to him, and what else can you advertise to this person? And that's the very practical case of using cluster analysis. I guess it's very often performed this way. So probably you want to know your customers, you want to group them somehow, and you want to do something with that groups, because that will give you some additional data of what can you advertise, what can you propose to them, and they will be more willing to buy that thing. The very similar thing you will get in, for example, some social networks like Facebook. Probably you will involve some sort of clustering analysis to classify your users into some groups. And depending on that group, you will try to target different advertisements to that group. Because, of course, you are creating that social network, for example, to make some money of it. And how do you make that? You make that basing on some sort of advertisement and so on. Probably you want your ad to be well targeted, and to get that targeting, you will more or less probably you will involve some sort of clustering analysis to classify all your users and to get some idea what can you show to them, and so on and so forth. Probably you can think at least of these sort of practical examples of cluster analysis, and maybe you will even sometime you will use something like that. Of course, you can use cluster analysis in different setups, and you can use that in some sort, I don't know, when you are doing some scientific research. So probably you have some data, and that cluster analysis may help you to get some insights into that data. Because we all know that if data is multidimensional, there are no chances that we can plot that and understand what's happening to that points. And if for some reasons reduction of dimensionality does not work, maybe you can try using some sort of different ways of analysis, and cluster analysis may hint you that there are, I don't know, some two blobs of points, and you should classify them and treat them separately. That may be perfectly the case. Okay. Here we go again with the idea of test-driven development. I have previously told you about this method. It is sometimes, at least, it is used when you are developing some software. And, well, not even regarding to some software, it may be a good idea to think about some tests for your method if you are developing some sort of method, or if you are even familiarizing yourself with some methods that was already developed for you. You want to have some sort of data set to test on it and to get some ideas of how that method works. Here are a few common data sets that you may want to use to test your methods, and to gain some insights in which cases these clustering methods are good, which cases they are not very good, and what should we do with them at all. Maybe the simplest case is just these three blobs. So we all are expecting for our clustering methods to find three clusters here. When they are some sort of distorted, some methods probably will have problems with that. And I guess we will already have some problems with that with k-means. But in the next lecture, I will show you some different method called GMM, or Gaussian mixture model, and that will do the job. Here is much more complicated two cases, like these two rings and these two, I don't know, half moons, or how do you call them? It's much more complicated to get these two clusters to be separated. But anyway, there are some methods that are able to do that. For example, spectral clustering is able to separate these two classes. If we have some time at the end of the lecture, maybe I will tell you a few words about spectral clustering and show you how that works. Well, and here is a very simple case, just a square filled with points. Of course, we would like to have one cluster here, but depending on the method, there may be some problems with that. Getting to practice, we have our data sets that we are testing on, and let's try to use all different methods that we have in sklearn on that data sets. So it's just to give you some sort of feeling, what instruments do you have in sklearn and what quality of the result do you get if you use them on these data sets. Here is k-means version, so mini batch k-mean, and you see that in here we have some sort of problems with that in some cases. In some cases we do not have. So the simplest case is pretty okay. Some other cases are, well, not so okay. Here are some different methods like affinity, prop, mean shift. Here is spectral clustering. You see a very powerful method that is able to undo this, to untie this knot of clusters and separate these two rings, for example, and these two half moons. And it's pretty okay with many different data sets. Some more methods like word, agglomerative clustering, dbScan, and optics, two quite similar and simple methods that do very well, I guess, on these data sets. And we have Birch and Gaussian mixture. So Gaussian mixture we will consider in the next lecture. But anyway, yes, please. Black points in optics and dbScan, they are not classified. These methods, they work, let's say, quite simple, I guess. Let me draw that on the whiteboard, so why not? Let's do that. Their basic idea is something like following. So I have here my plane. Here are some of my points, my data points. Let me say I have some cluster in here. I have some cluster in here. And what basically dbScan and optics are quite similar methods, so almost the same method. But what they do, for example, we have, let's say dbScan. We have two parameters for this clustering method. These are some radius r and some number m. And if I'm taking some point in here from the data set, I'm taking this point, for example, I'm taking this radius r, so I'm taking this radius r around this point, and I'm counting the number of other points that are getting inside of this radius. And if this number is greater than the value m, I'm saying that this point is a core point. So this point should belong to some sort of cluster. So I prescribe to this point, let's say, I don't know, I prescribe that a cluster blue, for example, and I prescribe that cluster to all the points around it. Then I'm taking each of these points, and I'm looking, for example, this one, and I'm looking once again in the radius r around this point. Do I have enough points for it to be a core point? And I do that so on, and so on. And the idea is that at the end of the day, I have some of these points, a cluster prescribed, and I have I know that they are core points. That means that in the radius R around each of these points will be at least m other points. Other points are densely enough packed around these ones. And then I will do the same for each of the points. I will just try it. I will just check what happens. And I will either know that it's a core point and I will grow a cluster around it, or I will know that it's not a core point. And the thing is that if I have some lonely point somewhere, for example, in here, I'm seeing that there are not enough points around it for this point to be a core point, and there are no core points around it to endow it with their cluster. So it remains unclassified. So it remains unclassified because you can propagate the cluster, so that prescription of points to some sort of cluster, you can propagate that just starting with core points. And core points should have enough other points around them in that radius R. That is the situation when you can have some points unclassified and you don't know basically what to do with them. So they don't have enough other points around them. They just remain as some sort of outliers. So you don't prescribe them any class. And you can check that for DB scan. If you look, you see all these lonely points around these clusters, and you might guess that these lonely points, they are not just passing that threshold. So when I'm growing that radius R around them, I see that there are not enough points around them in this case. Optics works very similar, but well, you see that DB scan has some minus to it. There is a problem when you are prescribing a cluster to the core points. Everything is okay. However you start, whatever you do, they always will be getting different clusters, and they will be clusterized correctly. But when we get to the problem of prescribing a cluster to the points that are not core points, maybe you will see a problem in here. So how do you think, what may happen if we have some point that is not a core point and that lies near to clusters? So I'm growing two clusters, I have some core points, and there is one point in between them. Yeah, you're right. So it wouldn't know definitely where to classify this point. And we are saying that in case of DB scan, the result for non-core points may depend on the order in which we are considering that points. So it's, in some sense, it's random. Optics is almost DB scan, but people tried to fix this issue. So they try to do something with the order of points, so at least you can have your results consistent. It's not like something very much changed. We are just trying to get more consistent results. So there are some tweaks to the DB scan algorithm. That's what we have. I guess in all the different methods that we have in here, they don't get some points unclassified. So probably these are the only two cases that we have. Okay. What now? Now let's introduce to our method that we will consider today. It's k-means, a very simple method, but I still think that we should know about it, despite that it's quite an old method and quite a simple. But anyway, simple methods are, first of all, easier to grasp, And the second thing, it's in some sort, this method is relative to the method of Gaussian mixture model, so probably it's nice to know about it. And maybe even the third reason, if we are considering, I guess, the most powerful of all these methods, like spectral clustering, there is a step in spectral clustering that involves k-means. That may sound a bit strange because you have a clustering method that involves different clustering methods, but that's the way it works. So maybe if we have time, I will show that to you. What about k-means? So that's a method that was used for vector quantization. It's originally comes from signal processing, and it's very popular for cluster analysis in data mining. So this algorithm is trying to put our n observations into k clusters. The number of k should be defined by hand in some sense. I will show you a few methods how can we guess it more or less reliably, but anyway, the vanilla k-means, if you are implementing that, you will have external parameter that you should set, and you should define the number of clusters that you want to get from your data set. This method was originally proposed in 60s, so it's quite an old thing, and it was used for quantization problem like color quantization. And I will show you an example of color quantization and how that works. Okay, so here is the case that we are trying to consider. So here I have generated few blobs of points, and we will try to cluster these blobs of points and get, of course, 4 clusters. What I'm trying to do here, I'm trying to perform k-means on these clusters. I guess I should start this part of code. And I will try now to change the parameter, the number of clusters, and we will look what happens when we are trying to cluster all these points with different number of clusters that we want to get at the end. Here you see the code is quite simple. I'm just using k-means that is imported from sklearn cluster. And well, I'm just creating this object, telling him how many clusters do I want, and I'm performing something like fit and predict. So everything quite simple as for different methods of sklearn. Let me try to change. Here is the case of 4 clusters. You see that k-means works perfectly in this case. Let me try to change the number of clusters, and we will look what happens. Of course, we will get some incorrect results, at least from our point of view, but I want you to know how that looks like, because in many cases it may be some sort of problem to get the perfect number of clusters in your data sets, and you might want to know what happens if you don't get it right. So here is the case of 3 clusters. Well, I think it still looks pretty reasonable as for me. So we have a cluster here. We have these 2 clusters merged into one in here, and we have 1 cluster here. I'm trying to get down to 2 clusters, and now I'm getting down even to 1 cluster. Well, that was quite obvious. Now let's try 5 clusters. So here we have 5 clusters, and you see the result. So one of the clusters was divided into 2 parts. Still, we have this. And I can try even 6 clusters. So 1 more cluster will be divided into 2 parts. So that's what we have. So now you more or less, you know how that looks like if you use k-means on some simple data set like 4 blobs, and you know how that looks like. These points, these are the center of masses of these clusters. You might guess that the word mean something means in the name of the method. It really means that you are calculating the mean value of your data points, or in some sense, it's center of mass of that data points. And of course, we will be concerned with that value because that will help us to basically run our method. Okay, now let's get a little bit more into details, what we have and how this method basically works. So I guess we have some issue with camera. Okay, so now let's consider K-means algorithm in a little bit more detail. So let's get to that mathematics that we have in there and how that basically works. Let's start with the function that is known like inertia. So here is the expression for that function, and here is one more expression for mean value. These expressions might be very familiar to you, but there is one component, this aij, that you might think, where does it come from? So this aij is basically they are basically components of the matrix that is performing prescription of points to the clusters that we have. So this is k-means. So we have already stated that we have k clusters, and now we are trying to put points into that clusters. So let me draw that on a table once again, just to illustrate this point. So my components A, I, J, they are components of the matrix that I'm creating, let's say, the following way. Here I have my clusters, so cluster 1, cluster 2, cluster 3, and so on to cluster K. So K means K clusters. Here are my data points. So I have here, I don't know, some 0.1, 0.2, 0.3, and so on up to, I don't know, point n. So these are my points. And if I am prescribing, for example, 0.1 to cluster 2, I'm saying that I have number 1 here. So here is my number 1, and this is my point. So if I have A, I, J, these are my parameters living in this table. I will say that, for example, this parameter, this I corresponds to the point I have. So that will mean that I 1, 2 will be equal to 1, because my point 1 is prescribed to cluster 2. Of course, you might guess that if I am prescribing some point to some cluster, I will expect that it's not prescribed to any different cluster. So here I should have zeros. And that will be the case for each point that I have in my data set. So for example, point 2, I can say it belongs to cluster 1. Of course, it does not belong to any other cluster. My points 3, they belong to cluster 1 as well. And so on and so forth. And if I'm having this matrix with all this information incorporated into this matrix, I can calculate some things more or less easily, because these parameters, they are helping me to extract some points that belong to some sort of cluster. So I may consider, for example, some row of this table, for example, this row 2, That means that I'm considering all AI2. That will take me this row. And that will mean that I can extract some sort of information from here. I can calculate, I don't know, the number of points that I have in cluster 2. How do you express that in some sort of mathematical notation? Recall, I have 1 in this case if the point belongs to the cluster, and I have 0 if it does not belong to the cluster.
Just sum the row.
Yeah, so I can just take a sum of the row, and I will have the number of points that belong to this cluster. So if I want to have some number of points that belong to cluster 2, so n2, for example, n sub 2, I can say that is just a sum over I of a I2. If I want to know the number of points in the J's cluster, I can just take a sum over I, a, ij. If I want to get a mean, if I want to get a mean value of the points in a cluster, what should I do? How do I express that mathematically? So once again, we can use this table. So this table, it prescribes points to clusters, and I can use that to calculate something. So if I know that all these points, they all belong to some cluster, to calculate the mean value of these points, I will basically do what? I will take all these points, I will add everything up, and I will divide that by the number of points that I have in this cluster. And I will get some result somewhere here. Now please think, how do I express this in, I don't know, in terms of this matrix and all that sums? So I want a mean value for some cluster G. So what do I do? So in the denominator, I should have the number of points in this cluster. So we already have it. So what we will have in the numerator? So we are calculating mean of these points. So mean is some sort of sum of everything divided by the number of that everything. The number of points is easy to calculate. You already have told me that we can just take a sum over the row of this table, and that will be okay. So I will get it. So I know what is my denominator. But what's now in the numerator? So I have xi Yes, absolutely correct. So what happens in here? So thanks to the matrix A, if I will take a sum over all x's that I have, and I am considering, for example, cluster 1, I will have Aij equal to 1 in here and equal to 0 in here. So if I am considering, well, I don't know, let it be cluster 1, and this will be cluster 2. So when I am considering Ai2, I will have that equal to 1 for each of these points. So this will be equal to 1, this will be equal to 1, and so on. And I will get equal to 0 in here. So this will be 0, this will be 0, this will be 0, and so on. So when I'm adding everything up, this part just disappears. I don't have it. And this part remains. And of course, all that Aij, they will be equal to 1. And we will get just a sum over all these points. And divided by the number of these points, I will get my mean value. This is quite a, let's say, simplified case in some sense, because we will consider in a future method that does not restrict ourselves to ones and zeros, but allows to have some sort of different numbers in this table. So we will have a very similar case. I will show that to you in the next lecture, that basically uses the same methods, but this table will be not so restricted. So that will be very helpful for us. Okay, here is a small mathematical notion for you, because these matrix, this parameter Aij, they can be called indicator functions, or sometimes called characteristic functions, or Boolean predicate functions, and so on. And I want to show you a few designations that you might see in different books for this sort of parameters. So it's this one, or it's chi of subindex A of x, or I of x, and so on. Or maybe even Iverson bracket, you might see that as well, and so on and so forth. It's just some sort of indication that x belongs to some set A, or it does not belong. If it does, this function gives you 1. If it does not, it gives you 0. Very often seen, and probably you will need that in some future. Okay, now what we have. As I told you in previous lectures, all our methods of machine learning, they boil down to some sort of minimization or maximization of something. And in this case, we might ask ourselves, what are we minimizing, or what are we maximizing? What do we want to have at the end of the day? And here is within a cluster sum of squares, this is our loss function that we will want to minimize. You may recall that this expression, it has to do something with the inertia that we have in here. So we are summing all these VCSS. So we are summing them to get the overall inertia. And in some sense, that means that if you have this sort of clusters, so you have these points, you have decided that you need to find 3 clusters, you are separating these points into clusters, you are calculating that mean values, and you are calculating the inertia of these points with respect to the center of their cluster. And you want that sum to be minimal. From a little bit different point of view, you can think about it like variation. So we all recall that there are few things very tightly connected, and this inertia is connected to the variation. You have very similar formulae. You might think of it like you want to have clusters and some sort of mean values, and you want your variation of points around their mean value, you want it to be minimal. And of course, if you have few clusters, you are saying that you want the sum of their variations to be minimal. That's what we have. Okay. Now we want to minimize this function L, and we want to minimize it with respect, of course, to that mean values and to the matrix A that we have. Of course, we are mostly interested in matrix A because that will prescribe that points to clusters, and that's what we want at the end of the day. In practice, please remember that we can always obtain only the local minimum of the function L. Okay, now what I want you to show are few algorithms. But first, okay, let's look at this, and then I'll show you that. Depending on how do you implement your algorithm, you can use one of at least few approaches, at least the ones that I know, and probably you can think of some more. How do you find the minimum of this function L with respect to all that mu j and a ij? The problem is that it's really complicated to do that simultaneously. You can just write some equations and get some formulae that will give you the result. So just to plug something in and to get the result out. It's not the way it works. So I want you to know that there is some sort of, I don't know, do I call that an approach or something like that in these and many similar cases. If you have a function that you cannot minimize at this point, it's very often used an approach of minimizing it iteratively with respect to some subsets of its parameters. In this case, we will be performing some sort of minimization in a loop by recalculating first centroids, so that's our mean values, that's our mu, and then repartitioning our sets. So that will be true for all the algorithms that we will consider. So we can't in one step get all mu j's and all a ij. So we will be doing that iteratively. We will find somehow some approximation for a ij. We will update our mu j, then we will update our a ij, and so on and so forth. So this is some sort of snake that's trying to bite its tail. So we are always doing that in a loop, and we have a hope that these updates will help us to get to the correct result, or at least to some sort of local minima. Okay, now let's consider the algorithms. So first, the most simple and the oldest algorithm that we have is the k-means by Forgy and Lloyd, 1957, 1965, so quite an old algorithm. So what do? First, of course, we choose the number of clusters. That will be true for all the algorithms, so we should predefine that before we do any minimization. Choose the method. Well, pretty reasonable. So we have some points in some multidimensional space, and we want to define distance between them. Of course, it can be some simple Euclidean distance, or it can be something else. So that depends on what you are considering. And then we choose some method to pick initial centroids. Once again, we should somehow prime our algorithm. It cannot start from scratch. So we should put at least do some approximation for our mean values mu. And that can be done in a few different methods. I will tell you a bit later which one do we use. But for now, think that you have somehow thrown that few new values in the plane, and you have some initial approximation. Then we are doing a cycle, and in this cycle, we are trying to do the following. We assign our data point to the closest cluster according to the metric. Then we recalculate the centroids. So I have thrown somehow these centroids in plane. I have collected all the points around them and prescribed them to that cluster. Then I am trying to update the centroids basing on the points that I have prescribed to them. I guess I will try to search first for a nice picture for you. Here is, for example, here is the case. Because I don't want you to be in some sense of confused, because that may be a little bit counterintuitive. So you might think, if I have somehow chosen centroids that mean values and I have prescribed points basing on that centroids, why on earth would I have any updates to that centroids in the future? And here I want you to show just some simple case how that works and why you will have some updates and what will happen. So here is the case. Here are my points. Here are some clusters of my points, and I have thrown in here 4 centroids. So I want to do k-means with k equals 4. And what do I do now? First step, I am prescribing these points to the centroids. So I'm just taking each point. I'm looking which one of these tentative centers is closer to that point, and then I am giving that point label of the appropriate cluster. So what will happen now? Now I have a bunch of points prescribed to these centers, but I guess you can definitely see that these are not the true mean values for the points I have prescribed to them. So there is really a reason to update them. And I'm doing a step. I'm doing a step in the update. So now you see I have changed positions of these mean values basing on the points I have prescribed to them. Now we look at this once again, and we think, well, can anything change right now? Probably yes. Because now we have changed positions of our centers, and if I will perform once again a prescription of points to these centers, something might change. For example, some of these points might get closer to the green center than to the yellow center. And maybe they will be reclassified into the different cluster. So let's look. So here something is reclassified once again, and here again, and again. And now you see how everything settles down in this position. So nothing changed between step 6 and 7, or almost nothing changed. Probably we might guess that we are in some sort of local minimum, and we can stop our minimization. So here is how it works. So we are starting with the number of clusters. We are throwing somehow the tentative centers. So we are expecting centers to be somewhere there. And then we are performing this sort of update, like updating our matrix A that prescribes points to clusters, and then updating our mean values. So that's what we have. Okay. So now regarding these 3 algorithms. So what I have shown you, that's an algorithm of Forgy Lloyd. So quite a simple algorithm. What else do we have? What can change in these algorithms? You can use algorithm of McQueen, 1967. The first part is quite similar, choosing number of clusters, initializing them, so on and so forth. What's different? For all data points, we are assigning the data point to the closest cluster according to the metric. and then we recalculate mean values. If for 4G Lloyd, I was making some large updates, so I was changing that for all points. So first I was repurposing all points and reshuffling them with respect to clusters. In McQueen algorithm, I'm doing that just point by point. So I'm changing one point and I'm recalculating something. So not for all points at once, but for one point each time. And Hartigan and Wong algorithm, 1979. This algorithm is even more careful than McQueen algorithm. Initialization perfectly the same. What we do in a cycle, for all the clusters, we are calculating that VCSS for each cluster, and we are trying to move each point from one cluster to another, computing how does the loss function change. We are very, let's say, careful by moving our points from cluster to cluster. So it's really a very, very careful method. So you are just taking, each time you are taking one point, you are trying to move that from one cluster to another, and you are calculating does your overall function, does your overall loss function get better. If it doesn't, or it gets worse, you don't move that point. So a very careful algorithm. You can see that these algorithms, they all have their pluses and minuses. For example, 4G and Lloyd is quite simple. It's good for large data sets, but it has some sort of slower convergence, and it may create empty clusters. So that may quite happen. So when you have some center of the clusters somewhere lying, I don't know, away from points, and all other clusters, all other centers, they were able to get all the points for themselves. McQueen algorithm has fast initial convergence, but it's sensitive to the order that algorithm is applied to the data points. So you might guess that when we are trying to move each of the data points, it might happen that when we are moving one of them, that changes something, and some other data point now cannot be moved. And Hartigan and Wong algorithm has a fast initial convergence, and it has some more problems, let's say. Okay, a few more formulae. Here is the Lloyd's algorithm, but how do we see that from the mathematical perspective? Because I'm telling you about all these updates, but are we sure that these updates are really leading us to making our function smaller and smaller, and what do we get out of it? So here is the case. So I have the function L that I want to minimize. And what is doing this algorithm? I want to minimize that with respect to mu j and aij. Here is my assignment step. So I'm assigning aij 1 if j equals to minimal distance from xi and mu some j. Or I assign 0 otherwise. So in plain words, that means that I'm assigning each point to the closest center that I have. If aij are given, we can minimize L with respect to mu j. I can use the expression for my loss function, and I can just simply do the gradient. So I'm just performing all the derivatives with respect to mu j. So I consider my aij fixed. I'm doing all the derivatives, doing, and that's what I have at the end of the day. So solving that for mu j, I will have that new mu j should be once again mean values for the points I have prescribed to the cluster. So that's what we have. So actually, there's a formula that shows that if we calculate VCSS J of cluster Cj with respect to arbitrary points tau instead of mu j, we will have this sort of expression. And some of you, if you have studied some physics, you can recall what is this formula, and probably you might guess its analogy in physics. So what is that formula? For I'm sorry. Yeah, that's moment of inertia, but moment of inertia with a twist. Yeah. So here you see that this part VCSSJ with respect to mu j, that's a moment of inertia, but the axis I am rotating that around. It does what? It passes. Yeah, so in some sense, yeah. So if you have some axis that passes through the center of mass, you have some moment of inertia. And you have a theorem in physics that says if I'm taking some axis parallel to that, but not passing through the center of mass, I will have basically the same value plus this thing. So this mu j minus tau squared, so on. So like moment of inertia of the whole thing, but compressed to the center of masses. So it's some additional summand that I get in here. So, and of course it's positive, so it makes the overall expression bigger. So you can even think of that like from the physical perspective. So if you want to minimize that value, you will probably want to rotate all your points around some axis that passes through the center of mass. So here you have it in equations if you do all the derivatives and so on, but you can think about it like it comes from physics, and you think, well, I should rotate around some center of mass, but not around some different axis. Here is the scheme you have already seen. So it shows us that we initialize centroids, and until convergence, we update them and update clusters, partitions, and so on and so forth. So here we have mu j's are in agreement with points that belong to the j's cluster after the second step, and the correspondence is changed after the step 1. And so on and so forth. In short, if I want to draw some lines between all the 3 algorithms, this one can be called like do some changes and proceed with consequences. So I'm changing, for example, positions of my centers of masses, and then I'm proceeding with that new values. I'm changing my prescription of points to the clusters, and I'm proceeding with that. So big changes, big consequences, but that's what we have. So that's the algorithm of 4G Lloyd. McQueen algorithm. This one is much more careful, as this algorithm updates mu j every time any aij is changed. So if point is assigned to different cluster, you are recalculating the mean values of the clusters. So here is what we have. So we initialize centroids once again, and until convergence, we do all these changes. So we are trying to change, for example, A1J, then we are recalculating respective mu's, then returning back to changing some different A, and so on and so forth. So we are just jumping here and there. And in plain words, that means that we are trying to do small changes, and then we proceed with the consequences of these small changes. So in the previous case, we did some big changes. So a lot changed. It may have happened that each point has moved to a different cluster. It can be. in this case, we are moving just 1 point, so we are doing small changes, just a tiny nudge, and then we proceed with the consequences. Okay, here is some sort of perspective of Voronoi diagrams on this case. So here you see the center of methods that we have. And you remember that we are prescribing points basing on the distance to these centers. And you might see that in case of, for example, in 2D case, I can draw some lines that are separating regions in which all points that fall into that region will be prescribed to the respective center of mass. So here is the image of that. And this image will help us, for example, understand some things in the future. Here we have it. Does everyone know what is a Voronoi cell and where does it come from? No? Okay. Okay, so some know, some do not. Good. Let me draw a picture for you, a small picture, and maybe that will be helpful. Okay, so a very simple idea. So here is a plane. And I'm considering, let me consider just 2 points in here. So point number 1 and point number 2. And I'm just trying to classify all points of this plane basing on the fact to which of these 2 points they are closer. So how do you think, how should I draw the separation line between, in this plane, to some sort of split it into 2 parts that show me which points are closer to this point and which are closer to this one?
Like connect those 2 points, find the middle, and then draw a line orthogonal to that connection.
Yes, absolutely correct. So I'm drawing some line in here. So this one is perpendicular. And all the points that live in this, let's say, half plane, they are closer to this one. All that live in here, they are closer to this one. So this is very similar to the problem that we consider with our clusters. So when we have these center of masses, we are trying to prescribe our data points somehow, and we can draw this sort of separation of the plane, and we know that everything that falls in here, it should be prescribed to this point. Everything that falls in here should be prescribed to this point. This kind of splitting of the plane, these parts of the plane, they are called Voronoi cells. Of course, this is a very simple image, because if you have some more points to which that you are considering, some more centers, of course, you will have a much more complicated situation. And so there are some algorithms how to draw, how to split this plane more or less efficiently. So once again, if you have this thing, you can draw some more perpendiculars, and so on and so forth. So you can think about splitting this plane into parts, and each of these parts will be closer to some of these points. This sort of thing is used not only in k-means clustering, but in different cases of analysis, and it's even used in some sort of graphics. Some additional thing, you can think about this sort of triangle. This is a Delaunay triangle, and maybe you have heard about so-called Delaunay triangulation. So if you have many points, you want to create some sort of mesh of these triangles, so do them more and more, and things get even complicated if these points, they all lie on some sort of surface, and you want to somehow draw that surface. If you do some sort of graphics, you will probably meet with Delaunay triangulation, and you will meet with all these Voronoi cells. So probably you will have you will see that somewhere if you do some, I don't know, some graphics or something like that. Okay, so here's what we have, and here is some sort of example of what happens if we are trying to fit with k-means so-called Mickey Mouse data set. So this is the case that we have. We are expecting these cells to look like this, but in reality we have something like this. So we cannot separate ears of the Mickey Mouse and get some meaningful results. So it doesn't work. And here is the reason why. In some sense, k-means is equivalent to fitting Gaussians with equals STD, and it's with so-called expectation minimization method. Okay. We can, here is basically the picture of that. So here is the picture of that. I have all these Gaussians. They all have equal STD. You see that we are working with the Mickey Mouse data set. And what we are trying to do, we are trying to fit them into that data set. And this is equivalent to the procedure of k-means. Here is a tricky question for you. Do you remember how do we call the method that helps us to fit some sort of distribution basing on the points that were generated by that distribution? Do you recall that from previous lectures? No? Emily, do you remember how what this means?
Maximum likelihood?
Yes, maximum likelihood estimation, that's it. So we are estimating the maximum likelihood basing on the samples that we have, and of course on some sort of family of distributions that we are choosing from. So in this case, if your family of distributions is some sort of sum of three normal distributions with equal STDs, you can perform the procedure of MLE, calculate all that maximum likelihoods, so on, and you will get this sort of picture. And if you do that, if you do all the formulae, you will see that it's equivalent to what we do with k-means. So basically that's some sort of k-means, but I know, some probabilistic point of view on that k-means, or statistical, if you wish, point of view. And this is the reason why there is such a bad problem with that data set with Mickey Mouse. So we have no instrument in k-means to change the STD of that Gaussian. So there is no way we can do that. So in this case, we would really like to have two Gaussians with some, I don't know, smaller or larger STD. So we want them to be more spiky. And the third one, we want it to be more spread out. But you see that we cannot have it in these methods. We will have the ability to choose that in the methods of GMM, of Gaussian mixture model, but we can do that in k-means. And that's the reason why it doesn't work with the Mickey Mouse data set. So I wanted to know about this issue and always to think, at least from this point of view, that you are trying to fit all that Gaussians and you cannot change their STDs. So that's the problem. Okay, the last algorithm, I guess, how much time do we have? Okay, so the last algorithm, then doing a break. Okay, very quickly. So Hartigan and Wong algorithm. So it's very careful algorithm that considers transferring each point separately. And just a note for you that you may think it's very long. It should take a very long time to transfer each point separately, because we should recalculate all that loss functions for each of the cluster. But it turns out that the formulae are so nice that I can calculate the change in the loss function L that we have basically on this formula. So here you see the old values of mean values, mu B and mu A. I'm transferring a point between clusters A and B. And here you see the point X that I'm transferring. And these capital A and capital B, they designate the number of points in that clusters. So when I'm transferring that point from one cluster to another, I'm just doing this sort of calculations. So I'm sort of multiplying by some quotients, this thing, adding, subtracting, and I get the delta. So how much does my loss function change? It's not a big deal to perform that computation, and you don't need to recalculate everything to try to move one point from one cluster to another. So it's really helpful. Yes, there is some additional information that you should keep track of, for example, the number of points in each cluster and so on, but it's not so complicated to do that, and it's really easy to recalculate our loss function. In this case, we can think about these methods like we are considering a small change. We are not even doing that. We are considering just a small change. And if this change is proved to be good, then we approve this change. So here is McQueen's algorithm. It's very, very careful. It just walks on eggshells. So it just tries to do some very tiny change, move one point. And if this change will be good, so we see that there is some sort of decrease in our loss function, then we proceed with the consequences. It turns out that the set of local optima of Hartigan's method is a possibly strict subset of the set of local optima of Lloyd's method and McQueen's method. And on average, we can expect that Hartigan's and Wong's method to provide an improvement by roughly 5 to 10%. So that's what we have. Okay, with that being said, let's take a break, and then I will show you how to estimate number of clusters that we have. So a break. Okay, let's continue. So we have already considered how to perform k-means clustering, and so even few methods, how can we do that more or less, let's say, carefully. Now we should let's say, consider a few questions that probably remain open at this point. So the question number 1, we have some parameters in our k-means method. So we are not starting from some sort of empty plane or just with the points of the data set, but we should, for example, choose the number of clusters that we will be searching for, and we should choose somehow some initial positions for that mean values, for that centers of clusters, so that we can start minimizing something. And we should somehow answer these two questions. How do we do that? How do we choose the number of clusters, and how do we prime them? So how do we choose their initial positions? Let's consider these problems, at least in some depth. In here, the number of cluster estimation. So I will show you two methods. The first one is so-called elbow method. So you can calculate L in scikit-learn using k-means inertia attribute. The number of clusters increases. If the number of cluster increases, then what happens to the inertia? So what happens to the overall L? Yes, it decreases. How can we see that intuitively? So what happens? We have some data set, we have some data points scattered all over the place, and I'm choosing a different number of clusters. So let's consider some extreme case. If I'm choosing the number of clusters that is, I don't know, equal to the number of points, you will have a perfect 0, because you can assign each point to its cluster and it will be equal to its mean value. So there will be no differences and no inertia. So you will have a perfect 0. And you might think for a moment, then when you are just increasing and increasing that number, the number of clusters, you will have smaller and smaller clusters, and that will, of course, make your function smaller and smaller. So you are always getting it smaller. So you cannot just minimize your function L and get some meaningful results about the number of clusters. So I mean that when we are doing all the calculations, we can minimize our loss function to get positions of centers of that clusters, and how do we prescribe clusters to the points to the clusters, but we cannot minimize that with respect to parameter k, because when the k gets bigger, we always get a smaller loss function. So that will be meaningless. But anyway, let's plot that function L. So here you see the values of L depending on the number of clusters. So here I have, I guess I should start first this part of code. Here I have my data points, and I'm trying to clusterize them. So when I'm taking one cluster, you see that I have value of my function L somewhere bigger than 2,000, 2,500. When I get 2 clusters, it rapidly diminishes to value somewhere around 1,000. When I take 3 clusters, it gets even smaller, and you see that I have something around 500. But when I get to 4 clusters, it still gets smaller to somewhere, I don't know, around 250. But any further increase in number of clusters, it doesn't make a very big change. Yes, the function is still getting smaller and smaller. So if I print out that numbers, I will see that numbers are always getting smaller. But we can see from this plot that starting from 4 clusters, the change in L is almost negligible. And the method of elbow, so elbow methods, tells you to draw this sort of plot. So try different numbers of clusters, look at the plot, and find the point when you stop that rapid diminishing of your loss function L. And if you find that point, you can say, well, this is the number of clusters that I want. So if you don't know how many clusters do you have, you can plot something like this. It will be always a plot like number of clusters versus the value of the loss function. So always 2D. And you can find the point when you stop the rapid diminishing, and your line just gets almost flat. Of course, you can think of some sort of criteria. How do you tell apart these two cases? So when do you think that it still gets smaller rapidly, and when do you think it's not getting so rapidly down? So yeah, there is some sort of problem with this method because it's a little bit ambiguous and it's not very reliable, but still you can use that in many cases, and you can get some idea how many clusters to use and so on. The other method that I want to show you is so-called silhouette method. It's a bit more, let's say, complicated, but much more reliable. So probably if you want to automatically compute the number of clusters, you may want to use the silhouette method. Here are the formulae. So for the point, some pi from the cluster Ci, we can define these sort of values. So this S pi is called a silhouette score for the point pi. And it is often drawn in some sort of silhouette plot. I will show. Well, that's how it looks like. So this is the silhouette plot. These are just small bars showing silhouette scores for the points belonging to each of the clusters. So here I have cluster 1, and all these green points belong to the cluster 1. I compute for each of them a silhouette score, and I draw them this way. This plot, when it's drawn, points are sorted with respect to their silhouette score. So their order along y-axis, it's not like having some meaning, but we are just sorting them to make the picture a little bit better. So because it doesn't matter how do you sort these points on a plane. And here is the cluster 0, many more points, and that's how it looks like. Okay, so what about silhouette score? So what does it do? So here is the parameter A that is calculating what distance between pi and pj for all points that are not, of course, equal to pi and that belong to the cluster Ci. So that's the mean distance to the points of the same cluster. BPI, what it does, once again, it calculates the mean distances to all the rest clusters and takes the minimal value. In some sense, you are estimating for each point how close is it to the points of its own cluster and how close is it to the points of some competing cluster. So you are not estimating that distance to the mean values. You may have done that somewhere. You have no mean, or you may not have any mean values at this point, but you have somehow separated your points into clusters, and now you are asking a question. So I'm taking some point, And I'm asking, okay, this point, it has some distances, some mean distance to the point of its own cluster. So how far apart are they? And there is some competing cluster that is close to this point. And I'm asking, what about mean distance to all that points? And my silhouette score is the difference between these distances divided by max value of them. And what do we expect out of all of this? So first of all, can you tell me this S of Pi, what is the range of values that it may have? Yes, it's from -1 to 1. A and B, they are always positive. So these are some sort of mean distances, so they are always positive. And if you have B much bigger than A, you have something close to 1. If you have A much bigger than B, you have something close to -1. Well, if they are more or less equal, it's close to 0. How do you think what these values mean in some sort of intuitive way? So if the value of silhouette score is close to 1, what it means? And that means, so what was B? No, A was distance to the points, the mean distance to the points of its own cluster. B was mean distance to the points of some competing cluster. So we considered all the rest clusters, we considered mean distances to all of them, and then we took the minimal value. So someone is better than the others, and it's like a competing cluster. So if we are close to 1, that means yes. So it's much further away from all the rest clusters than from its own cluster. So this point is, let's say, nicely classified, more or less. So because it belongs to its own cluster. If we have -1 or something close to -1, that's the opposite of the situation. We have, for whatever reason, the mean distance from the point to its own cluster much bigger than distance to the competing cluster. So maybe it wants more to be in the competing cluster than in this one. So this is the case when you get -1. And 0 means it's some sort of border point between two clusters. So you can't definitely specify, does it want to be here or there? So that depends. Okay, so what do we have now? In the example I will show you, we can calculate, first of all, I will show you this picture in a moment, just in more details. So SI are drawn in form of this horizontal and colored histogram that you see. The mean value of S can be calculated. So this mean value, in some sense, it tells us how good did we classify our points with respect to all that clusters, and we will look how can we analyze that. What else? Well, let's look at these images. No, let's look first at this thing. So here is mean values of silhouette scores and the number of clusters. Here is what happens. So if we have a number of clusters 2, we have silhouette score like 0.7. If we have 3 clusters, it's 0.58. Then it gets bigger when we have 4 clusters, and then it gets once again smaller when we get to 5 and 6 clusters. So we have 2 peaks like of the silhouette score at the number of clusters 2 and number of clusters 4. Let's consider the images and ask ourselves, are these results more or less meaningful? So here is an example when we have 2 clusters. And it looks, well, more or less meaningful, at least for me. So we have one very separate cluster here, and we have some big cluster in here. In case of 3 clusters, it doesn't look so well. And you see that in the silhouette score, how that looks like, and we have some smaller value in here. 4 clusters look meaningful once again, so we can really think about these parts like separate clusters, and it's really okay. And then we can get to number of clusters 5. We see that something went wrong. We will probably not want to separate this blob of points into 2 separate parts. And the same thing goes with number of clusters 6. When we see that we probably do not want to separate this or this into 2 parts. Yes, really 4 and 2 have some meaning, and we really can think that these are the values that we want to use. Okay, what else? The second problem I want to tell you is the initialization. Now we know how do we calculate the number of clusters that we are searching for, or after clusterization, we at least have some methods to assess how good did we choose that value. So maybe we can change that or something like that. But there is one more thing. To start all our algorithms, we not only need to calculate the number of centers that we will put in the plane, but we will also need to put them into some definite positions. So we should choose somehow where do we set that centers at the beginning. And depending on that, it turns out that we may have different outcomes. So in some cases, algorithm will get, let's say, slower. In some cases, we can get in some local minima that we don't want to have. Okay, so the problem of initialization is to form the initial K clusters. So many initializing techniques have been proposed from quite simple methods like choosing the first K data points. So you are just having some data set and you choose first K data points as the initial values for clusters. Very simple method, but probably you can guess the problem with that.
What if our choice is meaningless? What we've just chosen 5 cluster centers of clusters that are really close to one another. They must belong to the same, but we want to build something that will separate them and group other points around them. They'll be just
absolutely
how that would even work.
So if we have some data set and that points are some sort, let's say, sorted in the data set, taking first K data points, we will quite probably get them close to one another, and that may mess up the whole process that we have. The other way is so-called 4G initialization, that when you are randomly choosing K data points in the data set, that's much more meaningful because now you are choosing your points randomly. So with a higher probability, you will have your centers of clusters, you will have them separated and somehow scattered all over the place. That's okay, but that may have some minuses to its, of course, too. And it's not only if you are just unlucky and you are getting some points close, but you can think what happens if you have some large cluster and small clusters around. So it will be much more probable that you will get all your initial points in that big cluster, and probably that will mess up all the rest of the process of clusterization. So that may be the problem, of course. You can do that with so-called random partitions. So you are dividing the data points randomly into k subsets, and then you are doing something with that subsets, like calculating their mean values and so on. There are much more sophisticated methods, such as density-based initialization, intelligent initialization, first initialization, so-called FF. It works, let's say, by picking the first center point randomly, and then it adds more center points based on the fact how far are they from the chosen ones. So it tries to scatter the points all around the plane as far from one another as it can. And subset first, or SFF initialization, that's even more complicated things. Probably you should refer to some sort of papers. To underline the idea of this initialization and why are we concerned so much, I want to refer to the paper of Stanley and Brusco that provide a survey and comparison of over 12 initialization methods. So probably you might guess that it really changes the way how the algorithm works. So we really want some nice methods to initialize points to get some meaningful result. Maybe you can come up with your own method of initialization and so on. Okay, so here is some demo for you. I want to show you some very simple method of k-means clustering. Here is the algorithm. It's the simplest possible algorithm you can think about. Just that 4G and Lloyd algorithm. So here I am recalculating all that centers. I'm taking the distances to centers. I'm prescribing that labels to the points. So it's like calculating that Aij, and I am then recalculating all the centers and doing that in a loop. So that's a very, very simple method. You can see that you can implement that just in a few lines of code. And now I want to show you how that works in case of 2D space. Here are some points. I should initialize my method. So I should put somewhere some centers of clusters. So I should put them somewhere. And then I should ask to clusterize that. And now you see that when I started, I have put my centers somewhere here and here. Now I am prescribing each point to some cluster, basing on which one is closer to which center, and then I am updating my centers. So here is what I have. At the end of the day, this will be the picture I have. So 2 clusters and some sort of separation line. You can see that this setup is perfectly equal to the setup with 2 Gaussians. So here I have them, and if I'm doing a step, they are updating the values. What I want to show you more, let's say if I am choosing some not quite good position for all that centers, let's check what happens. Well, it still works, but now it needs, let's say, 2 steps to find positions for these points. Let's check that in 2D. So here I have my centers, and you see how the initial prescription of the points was performed. So all the centers have points from almost all the clusters. So when I'm doing a step, I'm moving them, and then I'm recalculating parameters for the points. You see that now they are correctly classified, and here they are now in the positions. Okay, so what happens if I am unlucky in choosing some sort of positions for my points? Let me try to do that in here. So for example, I have 2 points in here and 2 points in here. If I choose positions for my cluster centers somewhere in here, and I perform clusterization, I will get basically the result I have expected. So everything is perfectly okay. But what if I'm initializing them like this? So if I am unlucky and I'm doing this sort, and you might see that the method was quite unlucky. It created me an empty cluster. That's perfectly possible with the k-means. And moreover, it has classified all these points into one cluster. So you see that initialization, it's really important, and what you have may really heavily depend on how do you initialize your centers of clusters. Or you may have this picture when we are getting somewhere closer and we are prescribing these points once again to these clusters, but it's definitely not what we want. What we actually want is some sort of initialization that will give us something like this. So this is much more meaningful result. So here is that example in a picture. So please remember that this sort of initialization, that means. And here is even a case when you are using k-means from sklearn, depending on the seed, on that random value, I can get either a meaningless result as in here, or something even like this. So here I have like 4 clusters, and I will be expecting each of these blobs to be separated into one cluster. But what I get here is not what I expect. So please remember about it. And this is the case just of some bad choice of number of clusters. So that's okay. Here is one more example of how this algorithm fails. You remember the picture with the Gaussians, and you might guess, can this data set be separated in principle? And by k-means, no. So it cannot be separated by k-means. Why? In case of 2 clusters, how does the boundary look like? Yes, it's a straight line. And of course, if you cannot split this with a straight line, you cannot expect that k-means will separate that. So that's the case when it fails, and it will always fail. You can do some clusterization with different methods. For example, some, I don't know, spectral clustering or something like that. But you cannot do that with the regular k-means.
A lot of clusters like that, and then combine those additional clusters.
We can do something like that. For example, if we do a Gaussian mixture model, I will show you to you the case of these data sets when we are trying to cover them with a few Gaussians that really cover these to I don't know, half moons. But once again, everything depends on the problem you are solving. If you are trying to use that for clusterization, you will probably not want to have like 20 clusters in here, because we clearly see that we have only 2. Probably even if you do that, you will either need to find some method to clusterize your clusters, so to do some sort of aggregation of that clusters into something bigger, so that at the end of the day you get only 2 clusters. Or I don't know, come up with some other ideas, because yes, you can find some method to cover the thing with something and to separate that, but you wouldn't want to have 20 or 30 clusters in here. you need to glue that somehow in the future to get only 2. Okay, so here is just one more example. That's k-means from sklearn. This is more like example for you. So maybe you would like to play around with it. Okay, so what do I have here? I have fixed the number of clusters to 3. Okay, let's do 3 of them. So here is the result of how k-means works. So maybe you would like to play around with this thing and to try different configuration of the points to understand when everything works and when something stops working. So that may be a nice place just to play around and to gain some intuition on the k-means method that is implemented into sklearn. Okay. How much time do we have? 18 minutes. Okay, perfect. Very quickly, some sort of a variation of k-means, and then I will show you just a few examples of usage of k-means. Okay, so first of all, mini batch k-means. When we are working with some sort of very large data set, we can think about the computation time. So we can think, well, we need maybe some algorithm or some variation that will make our computation time smaller. We can use, in this case, we can use mini batch k-means. That's a variance of the algorithm that uses mini batches to reduce the computation time. Well, still trying to optimize the same objective function. So mini batches are subsets of the input data that are randomly sampled in each training iteration. And these mini batches, they, of course, they drastically reduce the amount of the computation because you are working not with the whole data set, but with just some random sample of it. And that really helps to reduce the time, and at the end of the day, you get almost the same result. So here is an example of k-means, the classical k-means, and mini batch k-means. It does something. It somehow separates the points, even in this quite ugly case, let's say. But anyway, it does something. And in the end of the day, if we compare these two things, and we somehow highlight the points that were classified to different clusters, you see that there are not so much points that were, let's say, misclassified, if you want, by mini batch k-means with respect to k-means. So it's a really nice method, and you see that mini batch k-means it should work much faster than k-means, just because it's working with some sort of small subset of the data set. K-medians, one more variation of k-means when you are using medians when clustering instead of using mean value. It has the effect of minimizing error over all clusters with respect to one norm distance metric, as opposed to a squared 2 norm distance matrix, with which k-means does. Of course, you can see one more benefit of using k-median instead of k-means. How do you think? What's that? If we are using mean value, we should be able to do what with the points of our data set? We should be able to calculate some, let's say, affine combination of that points. So I should be able to take some sort of numbers, multiply by these points, add them together, and so on. And if all these numbers, they add up to 1, I will say that's some sort of refined combination, and so on. So we should be able to do that. And in case of medians, I should only be able to sort that points. So I don't need to calculate some sort of mean value. I just need to sort them somehow, and I will know the median. So that will be enough for me. So once again, returning to the types of data we have, you are not always getting data in a sense of some numbers that you can multiply, add something, so on and so forth. So these operations may be meaningless for the data you have. But in some cases, you can sort that data and you can still get the median. So for some data types, these may be really meaningful change to change k means to k medians. Well, why not? K medoids, or partitioning around medoids, or PAM algorithm. So medoids are representative objects of a data set or a cluster with the data set whose average dissimilarity to all the objects in the cluster is minimal. So medoids are similar to means or centroids, but medoids are always restricted to be members of the data set. Probably you see the difference. When I was writing all the formulae somewhere up there, I was showing to you that the sum of the squared distances, when I'm minimizing that, the point to which that sum of squared distances is minimal is the center of mass of the points. But that center of mass is, in some sense, it's abstract. So it may coincide with some point in the data set, and it may not. In most cases, it will not. It will lie somewhere in between the points. And the thing is that if we add some more restriction, we will say, okay, I want the point which has that sum of squared distances minimal, but I just don't want to minimize over all the plane. I want to find the point from my data set to which the sum of distances is minimal. So I want to perform that minimization only with respect to the points of my data set. And that will give me the method of k-medoids. And that's really good because they are quite commonly used on the data when the mean or centroid cannot be defined. For example, if you are working with graphs. So if you are working with graphs, you have some sort of vertices. You can define distance between that vertices, but there is no meaningful value for the mean on the graph. So you have some edges, you have some cost to get from one node to another node. You can somehow define distance between two nodes, but you cannot meaningfully define some mean value of that. In this case, it may be quite useful to use this PAM method. First, it was proposed in 1987, so not very long ago, with L1 norm and other distances. So it's much more robust to noise and outliers as compared to k-means because it minimizes a sum of pairwise dissimilarities instead of sum of squared Euclidean distances. We remember that Euclidean distances, they are, let's say, tricky in sense of minimization. So we already have had problems with outliers with that Euclidean distances when we were considering, for example, linear regression and so on. So if we have that sum of squares, that really doesn't like all the outliers because it grows very fast. And k-means plus plus is one more variation and algorithm for choosing the initial values or seeds for k-means clustering algorithm. And it was proposed in 2007, really recent work by David Arthur and Sergei Vasilevsky. It's an approximation for the k-means problem. So here is some sort of pseudocode. What this algorithm does. Here is, so we have our data, we have defined the number of clusters that we want, and now we are trying to initialize something. So we are taking some random number and we are initializing our first mu, our first centroid with the value of the of some random data point from this data set. Then for all the rest clusters, so we are creating all the rest centers, and we are doing that in this way. So we loop over the data, we compute the distance from each of the data points to the cluster K, and what we do, we compute some sort of distribution, and we draw our center randomly depending on the distance to all the previous centers. So we like want our new center to be created somewhere far away from that centers, but it should be created at some point of our data set. So in this case, we are having I don't know, like some sort of balance. So our old created centers, they are trying to push our newly created center somewhere far away from them. On the other hand, if we have if our points are scarce somewhere there on the periphery, that will make the probability of getting that centers there smaller. So they are trying, so it's trying to get that center into the biggest blob of the points, and our centers already created, they are trying to push it away. Okay, there are some more methods, like you see, like fuzzy clustering, that allows these A's to be not only 0 and 1, but to change their value. There is Gaussian expectation maximization. We will talk about that in the future, and so on and so forth. So we have plenty of modification of k-means that's maybe suitable for different problems. Okay, now the last part, just showing you some really nice pictures, and I guess that will be everything I wanted to show you. Here is the NIST data set. We will be talking about recognition of handwritten digits. These are images 8 by 8 of digits 0 to 9. So nothing fancy here. So here how it looks like. Here we have it. And now what I want to do, I'm trying to perform k-means with the number of clusters equal to 10. And I'm performing this fit and predict. So what I'm doing here, this code is a little bit convoluted. So let me explain that in some sort of plain words. These pictures, you can consider them as the points in some multidimensional space. In that multidimensional space, I am performing clustering, and I want to get 10 clusters. I get these 10 clusters. So I have each of the points prescribed to one of that 10 clusters. Now I'm asking myself, are these clusters meaningful? In a sense, what do I want? What I would like to have? I would think that probably each of these clusters will correspond to some number, to some digit that I have in my data set. Of course, I do not know to which digit they do correspond. So that's, in some sense, that's the problem. So I may classify that to 10 clusters, but I'm not sure that these are zeros and these are nines and so on. So to show how good the clusterization was performed, I'm doing some, maybe you can think about it like some sort of cheating, but anyway, I'm considering what points do I have in there, what number is the most common in each of that clusters, because I know that after clusterization, I have my labels. And I'm saying, okay, let me prescribe the whole cluster to that digit. So to say that my clusterization predicts that digit if most of the points of that cluster were equal to that digit. And I'm trying to build a confusion matrix. And here you see the confusion matrix that I have in this case. And you might guess that this matrix is, well, not so bad, let's say. There are some, of course, there are some troubles. Here I see, for example, 1 and 8 are sometimes confused. But anyway, it's a really nice confusion matrix. So you might guess that if I just had that data points, I didn't even know what's in there, and I have somehow managed to clusterize them into 10 clusters, I will get some very meaningful clusters. So with a really high probability, I will get in each cluster just one number. And I have 10 clusters for 10 digits. So that's really good. Okay, here I try to do that with TSNE. I'm not sure why an error here. So maybe I should restart some code in here and in here. So this is a little bit more powerful method. So I'm trying to perform clusterization, but here I have transformed my data set with some nice methods to reduce the number of dimensions. So you remember I have already performed that in previous lectures, and we had that something still not working. Okay. It defined mode, but I'm not sure where did I define.
It was lower. Yes, here. Yeah. This.
Okay, let's try again. It very quickly gets outdated, basically, so you already see some warnings. It's really hard to keep up with all the changes. And here you see that we have a really nice accuracy of 94% when we are doing that after some sort of dimensionality reduction. Okay, so these were the numbers, and here is one more example, the last one for today, I guess. This is an example, I guess, the first problem that people tried to use to solve with the k-means method was the problem of color quantization. And here is an example for it. So here is some sort of picture, and it has quite decent amount of colors in it. So it's probably 2 to the 24, something around 16 million of possible colors. And I would like to somehow squeeze all that large color space into something much smaller. So for example, I want to convert that into 4 bits, so only to 16 colors. So can I do that? And if I can, what will I get at the end? So here I'm trying to perform all that things. Okay, I guess just disregard all the code. Let's look nice pictures. Here is here are the points from the picture. Of course, not all the points because there are too many points. It's just some random sample. So you might guess that if I draw all the points from the picture, it will look something like this, quite similar. Along the axis, I have levels of R, G, and B. So each of these points, it was some pixel in the image. I have taken that pixel, and I'm representing that as a point in the 3D space. So here is what I have. And now I want to try to clusterize these points into 16 clusters to get something out of it. And here is the result of that clusterization. So here are my 16 colors, and here are the clusters I was able to find with the k-means method. If I show only the cluster centers, so here are the centers, these are the points to which I will reduce each of that pixels, to which I will reduce each of the point of the cluster, of the big cluster. So that was my original image, just some sort of separated into pixels. Here will be my reduced image, so my new clusters, and I will change each of them to these centers. Yes, does it make any sense for you? Good.
Yes.
So now let's check what happens. And here's the result. Here is the original image, and here we have the 16-color image. Yes, it doesn't look so nice as the original image. On the other hand, it doesn't look very bad, basically. So maybe you have even seen these sort of images somewhere on the internet. So I don't know, but I guess in 2005 or even in 2010, these images could be still found on the internet here and there, and probably you remember that problem with the gradient in sky and so on and so forth. Yeah, very good point. So if you are using some GIF format, you will get these sort of images, but a little bit better. Yeah, so we will get not 16 colors, but 256. So yes, details are certainly lost in the right image, but still the image is easily recognizable, and it achieves the compression factor, if you think about it, of 1 million. So that's a really high compression factor. So we have 2 to the power of 24, and now we have only 16 colors.
Actually, the compression factor is from 4 bits to 4 bits. So it's still with respect to.
Okay, why did I calculate that in such a way? Maybe when saving that to GPG, I don't know. Well, yeah, if we calculate the number of bits, it looks like not so many. Or I have something miscalculated. Anyway, we have some more or less large compression factor for the image, and the image is still more or less recognizable. So that's the way k-means was used in the early days. Now I'm not sure if anyone compresses images that way, because now we don't have such a big problem with all that space and memory and so on. So it's probably nobody cares. But anyway, in other places you can still see k-means, and it still works. Okay, I guess we are now running out of time, or I still have some. Yeah, but you should have some break probably. Okay, maybe if you wish, I can tell you just a few words on I don't know, spectral clustering, but that will be just a few words, I guess. Okay, so yeah, I try to squeeze that into 5 minutes. Have you heard anything about spectral graph theory? No, so just regular graph theory. Okay. Maybe if you're interested, you may want to check something on spectral graph theory because it has to do with that. But anyway, let's think. First of all, the spectral clustering is the clusterization on graphs. So we should have some graph. I don't know, let me put some nodes in here, some connections in that graph, I don't know. And well, let me put some different nodes in here and some more connections in here. So here is some sort of my graph G. And if we want to perform some sort of clusterization, there will be there will be two questions. So first of all, how did I get from my data points into here, so to this sort of graph? And you probably might guess at least one very simple method how to do that. So you have some data points, you want a graph out of there. So what do you do? Yes, so you can connect that to all points that are closer than some distance. You can define some distance epsilon, for example, and you can connect everything that is closer to that epsilon, and you will get a graph. Or you can try to use some sort of graph with weighted edges, and you can connect everything to everything, but you can define that weight on the edges, bathing on the distance between points. So at least two methods. Let's go with the first one. So I have chosen some epsilon, and I have connected my points, bathing on the fact, are they closer than these epsilon, or are they further apart? Now the problem of finding clusters has transferred to the domain of graphs. So previously I had just bare points. Now I have graphs on the plane. And here I'm asking a question, how do I find these clusters? That will be basically my connected components of the graph. So that's simple. I have a graph, I have connected components, and I can search for them. Probably you know some algorithm to find connected components in the graph. So which one do you know? Let's say some sort of, I don't know, some breadth first search, yeah, or some depth search. So whatever you do, so you can think about algorithms that will find you these connected components. But now comes the problem. It's okay if I have graphs like this, and each of my, let's say, cluster corresponds to a connected component. But what will happen if I have some connections that basically connect me some different clusters? So for example, I have a lot of points in here. So let's say I have a lot of points in here. I have some sort of edges, some more edges, and so on and so forth. And I have some points in here. And here is some sort of, let's say, parasite point that creates me edges here and here. And this is really problem, because if you are doing all that breadth first search or depth search or so on, if you are starting with one of these points, you will sooner or later, you will get to this point, and then to this point, and then to all of these points. And you will collect everything in here into one cluster. But you probably don't want that. You probably want these points to be separated into one part, and these points to be separated into a different part. And this is the problem, because our discrete algorithms, they don't allow us to understand how tightly are connected points in some part of the graph. So we want something that will tell us how tightly are the points in here connected to one another. And there is a very interesting method to do that. It's basically, let's say you are creating two matrices. So matrix W. And in here, you are putting, let's say, zeros on the diagonal. So my diagonal will be zeros. And here you are putting ones and zeros depending whether your point I and point J are connected or not. If they are connected, you put 1. If they are not connected, you put 0. So some sort of adjacency matrix. This is my W. The other one matrix will be matrix D that contains, I guess, the sum of squares let me think it. The sum of squares of weights that we have between points I and J. So this component, let me call it W, small w, I, J. So here it is. So this is my W, I, J. Here for each point, let's say I, so this will be diagonal matrix. I will have sum over OJ, WIJ squared. And so on. These I have on the diagonal. Here I will have zeros. So this is what I have. And I will construct a Lagrangian matrix that looks like, I guess D minus W. This will be my Lagrangian matrix. It still may look some sort of obscure for you. So what I'm doing in here, so it's really strange, but the problem is I don't know the shortcut or some intuitive way to see through all these things. So we should build some sort of mathematical apparatus and then just move further. So here is a very interesting object that is explored in the spectrograph theory. And it's called spectral because I will consider this matrix L and I will ask a question about its eigenvectors and eigenvalues. And I'm especially concerned about its eigenvectors that are connected to the eigenvalue 0 of this matrix. So I'm acting with this matrix. I can act on some vector, let's call it Fi. So this will be the vector. These are, I'm considering them as some sort of operators. And I am very interested in the case when this is its eigenvector and it has 0 eigenvalue. Why am I so concerned with this thing? So let me multiply it by F transpose on the left side. So this will be my Fi, say transposed L Fi. This is quite interesting expression that we can think about. So what it gives us, this expression. So first I will expand this thing. So this is Fi transposed D Fi. I'm just using the linearity. Then Fi transposed W Fi. Here is my expression. Now, what can I get from here? This is a diagonal matrix. It's very simple, yeah? So when I'm multiplying this thing by Fi in here, I'm just getting a quotient Fi some component of that fi multiplied by these values on the diagonal. Then I am multiplying by the transposed, and I make them, I get them up to the squares. So here I expect something like what? W I J F. Okay, I don't like the way I wrote this because I have put here an index I to show that these are some, not one vector, but few vectors. Let me remove this index for a moment because I want to use that with the components of the vector f. So let me remove it in here. Let me remove it in here. And let me say that if f is a vector, then fi be its component. Let's do it this way. So here I will have fi, I guess, squared, this thing probably squared, and sum over I and j. What do I have in here? So I am multiplying my w by these vectors f, and I'm having here some quadratic form. So here will be some sort of, once again, some sort of sum. Once again, I get wij, and I will get here f component I, f component j, sum over I and j. Well, looks pretty reasonable. Now let's do a few more transformations, and we'll see what we can get out of here. Just one thing to remind you, this matrix W, how do you think? Is it symmetric or not? Just basing on the fact how we build it. Yes, you're right. So it is symmetric because if I is connected to J, of course J is connected to I. Why wouldn't it? So I can write this thing in a similar way, like W squared IJ F J squared. So I want you to notice this equality. And this equality means that I can write 1/2 of this sum. I can write as it is ij wij squared fi squared plus sum over ij wij fi and j plus 1/2 sum ij wij, I guess, squared, or I shouldn't square it. Well, let's see. And here, well, maybe I don't need to square this ij. Okay, maybe not. Maybe I'm doing that wrong. Okay, so I don't have square in here, and in here. It doesn't really change anything, but we'll need that. Okay, so we have this expression. What do you see in this expression that some sort of transformation you probably would like to perform? What do you see in here? So what's that? Do you see the square of a sum in here?
Yeah, it kind of looks like dot product
I can take
somehow.
out this 1/2. Yeah, I can take
Yeah.
out this 1/2. Here all are sums over ij. I can take the sign of sum. I can take it right here. Yeah, because everything is linear. And I can take wij. Wij. And in here I get fi squared. I guess, why do I have plus here if I have minus here? And nobody has told me, yeah? Minus. I have 1/2 carried away, so 2 fi fj plus fj squared. So now it's much more obvious, yeah?
Yeah.
So here we have it. And now what was everything about? So I am having this expression, but I am concerned about f that is eigenvector with eigenvalue 0. So these all these things should be equal to 0. And now you tell me, when do we have this thing equal to 0?
When
What
either
should
W is 0 or those in or Fi equals Fj, yeah.
Yes, absolutely correct. So here is the case that we have. Basically, I will just reiterate. So these wij are taken from this matrix, and they are positive, always. This thing is a square. It's positive, always. So to get 0 from all these sum, we should have each of these things. Well, doesn't mean which I and j we take. It should be equal to 0. So if this part is equal to 0 for some I and j, that's either wij is equal to 0. That's quite possible. So we have ones and zeros there. Or we have fi equal to fj. And this is a very crucial part. What it means, if we have some vector f that is eigenvector with eigenvalue 0, that means that either between I and j, there are no connection. So no connection between I and j, or fi is equal to fj. So if I have some points in here, and I have two different clusters, so for example, I don't have this parasitic node, my W matrix can be represented in the format of two blocks. So I will have one block for the cluster A and one block for the cluster B. So one for A and one for B. And if that happens, you can think about eigenvectors. You can think about these f's that you can find such an f which have, for example, ones corresponding to all points from the block A and 0 to B, and from some f that has all ones corresponding to B and zeros to class A. So in your vector, you are somehow doing like checkboxes that tell you to which cluster your point corresponds. It's a little bit more complicated than that, but let's stick with it. So your vectors are, in some sense, are characterizing your these connected components. I think it's a bit more complicated because if you have eigenvalue 0 and few eigenvectors connected to that, you are basically extracting the subspace from all of there. So you will need to do some more work to understand which points correspond to which block. But you can do that with these vectors. But now what happened? Previously, our algorithms were giving us some sort of discrete result. So either there are no connections and we have these two components, or there is some connection and we cannot separate them into two components. Now you tell me what has changed in this case when I'm calculating all these eigenvectors and eigenvalues. A very similar thing we had when considering linear regression, when we have some sort of linear equations and we know how to solve them when we have that equal sign. When we have some sort of approximately equal, we didn't know what to do, and we had to transfer to some different problem. Here is a very similar case. We don't know what to do in this discrete case, so we should transfer to some different problem. And here is the place to perform that transfer. So when the eigenvalue is exactly 0, I have the same result as I would have with my discrete algorithms. But I can change it. Instead of 0, I can use some very small epsilon. And now my problem changes. With these small epsilon I can tell, let's say I can check these connections and say which connections are strong and which are not strong. So this is a way to transfer from that discrete problem when I was either taking everything here or not taking, to some sort of, let's say, not discrete, to some continuous problem with these epsilon. And now I can solve these cases. So these parasitic connections, they can be disregarded. I can still have these two subclusters when I'm using some small value here instead of some 0. And basically, that's the way that we perform it. So we are constructing this matrix, we are doing all the things, and at the end of the day, we have these vectors. I'm telling that there is a bit more to that, because when you get these vectors, I will remind you once again that I will have some random vectors that characterize me the whole subspace, linear subspace of that. And as an algorithm, I will collect them into some sort of matrix. So this will be my vector f, let's say 1. This will be my vector f2, f3. Well, how many do I get them from that fn? And in the rows, I will have some sort of descriptor of each point. So the values in here are describing me some point 1. The values in here are describing me some point k. And for points that belong to one of these clusters, I should have these descriptors being very close, so almost the same. And it's a really interesting thing that at the end of this algorithm, when you perform all these calculations, you have this matrix, you take these rows and you clusterize them with k-means. So you clusterize them with k-means, and you have clusters of, and you will know what to prescribe, to which clusters prescribe each of the points in our graph, or each of the nodes, if you wish. So k-means still lives in the spectral clustering. So that's what I want you to know. So at the end, you will have at least one step that uses k-means, so it still lives in this quite complicated and, let's say, convoluted method. Okay. Maybe you have some questions, especially regarding all these things, because I know they look quite convoluted. So probably if you have some questions, let me answer that. Or it's more or less clear what we have done. To think about it. Yeah. So the main philosophical point to break discrete problem, make it continuous. And you do that with transferring from 0 in here to some small epsilon. All the rest, it's just some sort of calculations that justify what we do. Okay. Anything else? Any questions, comments? No, nothing. Okay, then I think it's everything I wanted to tell you. So have a nice weekend and see you next Friday.